In this section, we're going to be talking about exponential functions. To start off with, we say f of x equals b to the x power is the exponential function such that b is greater than 0, b does not equal 1, and it's important to note that b is also a constant, so it's not a variable. And finally, x is a variable, and it is a real number. Okay, so an exponential function means that we're taking some constant, like 5, and raising it to a variable power x. So 5 to the x power would be an exponential function. Why is this useful? Well, graphs sometimes follow what we call exponential growth or exponential decay. So it's useful for us to be able to model those graphs using a function, just like we would model a parabola using a function based on x squared, a quadratic function. So the first type of graph we deal with, an exponential growth function, occurs when b is greater than 1. So when b is greater than 1, no matter what value it is, you are dealing with an exponential growth function, and it will look just like this red graph here. It will start at almost 0. It will never equal 0. Notice how it levels off here, and it'll quickly pick up, and then it'll suddenly start rising very rapidly to the point that it almost looks like a vertical line at its as it gets to its highest value up here. So it just shoots off to infinity very rapidly. And this general shape here is what you refer to when you say exponential growth, a very rapid rise. It's important to note that all parent exponential functions pass through the point 0, 1. They all will pass through that before you apply any type of transformation or translation to them. From here, exponential decay occurs when b is between 0 and 1, not equal to 0 and not equal to 1. So this looks like the opposite of what we were just dealing with. We start off at some very large number, and then it quickly decreases down to almost 0, but again it levels off. It will never actually reach 0. So we have some value way up here, and then it suddenly just starts decreasing very rapidly. These are very applicable to real-world situations. Half-life is an exponential decay problem. Exponential growth is modeled by money and viruses spreading, infecting. So again, this graph also passes through the point 0, 1. Its parent function does, no matter what b value we're dealing with. But as soon as we start applying any type of transformations to it, this point 0, 1 will move up or down based on what we pick. So typically when you're dealing with an exponential decay problem or exponential growth, you won't have both sides of this graph because typically your x value is time. So the graph will look something more along the lines of this or something like this. And I apologize if that noise affected this. Some motorcycles were passing by. Okay, but notice it doesn't always have the full graph, but this still represents an exponential decay. We started at some value here and then quickly started rapidly decreasing, or we started at some value here and then we rapidly started increasing. Alright, so from here, let's make note of the domain. Given both of these red graphs, what domain were we dealing with? Well, we started all the way to the left because of this arrow pointing to the left, And this arrow is pointing all the way to the right. Even though it's rapidly increasing upward, it is still always going to the right, which means the graph is from negative infinity all the way to positive infinity. The range, however, is all of the possible y values, and for both of these graphs, it's the same thing. They both are above 0 and can never reach 0, so we say 0 to infinity, not including 0, so we put a parenthesis with the 0. Alright, now at this point, let's go ahead and look at some functions and decide whether or not they are exponential functions. So looking at these functions, take a moment, pause the video, see if you can't decide whether or not these are or are not exponential functions. Okay, so trying this together, the first one, f of x equals 3 to the x. It's a constant being raised to a variable. The constant satisfies our rules. It is greater than 0 and not equal to 1. And because the exponent is a variable, this is an exponential function. Number 2, again, the constant satisfies its rules. And the exponent does represent a variable. X minus 4 is just some unknown number. So again, this is an exponential function. From here, we have negative 2 to the x. Negative 2 is less than 0. So even though it is a constant being raised to a variable, it is an improper constant that was chosen. This is not an exponential function. And finally, x to the third power. This is not an exponential function. This is a power function. This is just x being raised to a constant, which is the opposite of what we want. And now from here we'll talk about the two most common types of exponential functions. The first one is f of x equals e to the x. E is what we call the natural base. It's a number approximately 2.7. Think of it like pi. So it's just a very long number that's just going to keep going on and on and on forever. It's irrational, so we can't convert it to a rational number or a fraction. So we write e to the x. And the reason why this is probably the most common exponential function there is because it's very useful when you start working with calculus and you take derivatives and antiderivatives. E to the x is the easiest exponential function to take higher mathematical problems and apply them on it. It works out very easily, whereas every other exponential function is rather difficult to work with. From here, f of x equals 10 to the x is probably the second most common exponential function, just because it's based on everything we've worked on since we were little kids. Whenever you think about rounding a number, you think of rounding it to the nearest tens place or hundreds or thousands typically. And that's because our numbering system is based on base 10. So, for instance, if you think of the number 234.56, might as well. If we look at this 2, what does this represent? This is the hundreds place. It represents 10 squared. What does this 3 represent? The tens place. It represents 10 to the first. What does the 4 represent? The ones place. 10 to the 0. What does this 5 represent? The tenths place. 10 to the negative 1. And what does this 6 represent? The hundredths place, 10 to the negative 2. And we could go on infinitely in both directions. This number, our numbering system, is based on base 10. So that's why this is the second most common type of exponential function you'll deal with. And if you have a TI-84 or TI-83, if you look in the bottom left of that calculator, three buttons from the bottom left, you'll see an ln button. I apologize. If you look at that button, we're not referencing just the button itself. We are referencing the value above it. Above that ln, you will see an e to the x, and then the button above that says log. Above that in blue, you'll see a 10 to the x. These two exponential functions are so common they actually have their own dedicated buttons on these calculators that we use in pretty much every mathematics course across the country. So when we do these exponential functions, for the majority of them, e to the x and 10 to the x are the most common things you'll come across. So from here, let's go ahead and try some problems. So for this first problem, we want to find the exponential model f of x equals ab to the x such that it passes through the point 1, 6 and 2, 12. So this is a very real-world problem. You're given data and you need to model it to predict what will come after or what came before. So we have 2 points that we need to model into an exponential function. So the way we're going to do that is realize that these 2 points represent x and y values. So we're going to set up 2 equations, plugging each of these values into those equations, and then use a substitution method to solve these. So plugging in 1 for x and 6 for y, or f of x, we get 6 equals a times b to the x is now 1. And now for our second equation, 2 is now x and 12 is now y, or f of x. So we get 12 equals a times b to the x is now 2. So our 2 equations that we're dealing with are 6 equals a times b and 12 equals a times b squared. Okay, so now we need to use substitution. The way we're going to do that is by solving for either a or b and then plugging it into the second equation. I'm going to go ahead and solve for a. So I'm going to divide each side by b. I apologize if these b's look like 6's. It's a little difficult to draw here. So we get a equals 6 over b. And now when we substitute that into the right equation, we get 12 equals a is now 6 over b times b squared. And now simplifying this, if we put this b squared over 1, we have a b in the top and bottom that we can cancel out, leaving us with just one b in the top. So we get 12 equals 6 times b. And dividing each side by 6, we get b equals 2. And since b equals 2, plugging that back in over here in our equation for a, we get a equals 6 divided by 2, so a equals 3. So what's the exponential function of the form ab to the x that passes through these 2 points? It's f of x equals a, which is 3, times b to the x, so times 2 to the x power. Because we didn't put the 3 in the parentheses with the 2, it is not being raised to the x, only the 2 is. So this is our exponential function. Go ahead and take a moment. Try to find the exponential model of the same form, so ab to the x, that passes through the point 1, 6 and 2, 18. Okay, So trying this together, we again are going to plug in our y value for f of x. So we get 6 equals a times b to the x is now 1. And now plugging in 18 for our y value, we get 18 equals a times b to the x is 2. So 6 equals a b, and 18 equals a b squared. And we're going to go about this the same way we did before. We're going to divide each side by b to get a equals 6 over b. And from there, we can now substitute that into the right equation, which gives us 18 equals a is now 6 over b times b squared. Again, if we have a factor in the top and bottom, these b's in the top and bottom of our fractions, again, you could put this b squared over 1 if you prefer. We can cancel the b from the top and bottom, leaving us with 18 equals 6 times b, and dividing each side by 6, we get b equals 3. And now that we have b, we can plug it back into the other equation to get a equals 6 over b is 3, so a equals 2. So our a and b values ended up being opposites of what they were in the previous problem. We have f of x equals a is now 2 times 3 to the x. Okay, continuing on to the last part of this video, we have the formulas for continuously compounded interest and interest compounded over n periods. So, when you compound interest, it means that your interest is gaining interest. So simple interest is when you have $100 and you say, give me $10 when you pay it back. They gave you 10% interest. That's simple interest. Compound interest is like a credit card. Every day you put money on it and the interest builds on that money, and then the next day the interest builds on the interest that built the day before, and it keeps building up. So, the first formula for continuously compounded interest, which means basically every nanosecond you're gaining interest, is A equals PE to the RT, often referred to as PERT to memorize it. And from here, the formula for interest compounded over n periods, so that means if you have 10 periods in 1 year, every time that 10th period comes up, every time one of those 10 periods comes up, you gain interest on your interest. The formula for that is A equals P times 1 plus R over N, all to the NT. And now to go over what these values mean, we say A is the balance including interest after time t. It's the accumulated value. We say P is the original amount, or the principal. R is the annual interest rate. T is the time in years. It is very critical that that number is in years. If it's not, you have to convert it to years. And finally, N is the number of compounding periods per year. So some examples of N, if it's compounded monthly, then it's compounded 12 times per year. Daily, 365 times per year, not counting leap year. Quarterly, 4 times, semi-annually, 2 times, and so on. So with that, we want to find the accumulated value of a $100 investment over 36 years at a rate of 10%. If it is compounded monthly, and then if it is compounded continuously. So let's try out the monthly. We need to know what information we have. So we have A, P, R, T, and N that we're searching for. A, we do not have it. That's the accumulated value that we're looking for. P is the initial investment, which is the $100. R is the interest rate. That's the 10%, which in terms of a decimal is just 0.1. Just quickly showing that off to the side. 10%, whenever you want to convert a percent to a decimal, you just move your decimal 2 times to the left, which gives us 0.10 or just 0.1. T is the number of years, which is 36. And N, because it's compounded monthly, is 12. So putting all of this together, we have A equals P times 1 plus R over N is 0.1 over 12. To the NT is 12 times T is 36. And now there's nothing here that we can really simplify, so it's just a matter of plugging this into our calculator. And when you plug this into your calculator, you should end up getting A equals 3,605.63. So I'm a little short on room here, so I'll just go ahead and say this. Whenever you're answering a problem like this, you should give a sentence answer to explain what this value means. So for an answer on this problem, you would end up saying something along the lines of the accumulated value of the $100 investment after 36 years is $3,605.63. So I'll just go ahead and underline that because this isn't technically the answer, the sentence is. But again, just make note that you found the accumulated value from the original investment and how long it was is basically generally a good idea on how to approach giving sentence answers. With that in mind, we now have compounded continuously. Take a moment, pause the video, see if you can't find that. Okay, so trying this together, all of our information still previously works, the previous information works, that is to say, so we can just start plugging this into our formula. A equals PE to the RT. We're looking for A. P is 100 times E is just a constant. It's that number that's approximately 2.7. You would just look for it on a calculator essentially. So A is equal to 100E to the RT. R is again 0.1 times T is 36. And from here, we can go ahead and just plug this into a calculator. It looks a lot nicer to work with, and we end up getting $3,659.82. So for this one, I apologize if the typing is a bit loud, but I do want to go ahead and write out a sentence answer just to give a decent idea of what this should look like. So we would say the accumulated value after 36 years when compounded continuously is $3,659.82. And that would be the answer that we would want to circle for our final answer.